Hey there, it's Mrs. Allen, and today we're studying Chapter 2, Differentiation in Calculus. So we're in Section 2.8 of Related Rates, and we're going to examine related rate problems, and we're going to solve related rate problems. So you're asking yourself, what are related rate problems? Well, it has to do with how different objects or things are changing at rates that are related back to some equation or formula. So what I'm going to have you do is complete the warm-up, and the warm-up is 1 through 7, where you're going to be writing a formula for the given quantity, and then you're going to be finding a derivative with implicit differentiation, the topic you just finished in 2.7. So pause your video, complete the warm-up, and then start it back up, and then review your answers. Okay, so now that you've paused your video and you've completed the warm-up, in this section you will study problems involving variables that are changing with respect to time. If two variables are related, those variables' rates of change are also related, therefore the topic related rates. So here are the answers for the related rates. Of course, your formulas for area of a circle, volume of a sphere, surface area of a cube, volume of a cube, volume of a cone, area of a triangle. So those are all equations, and we could say that, for example, the first one, a radius of a circle is changing, and how is that affecting the rate at which the area is changing? We'll be looking at that. And then for your final problem, you're finding dy dx with implicit differentiation. You have dy dx is equal to 2x minus 3y over 3x. Okay? So in this section, you'll study problems involving variables that are changing with respect to time. If two variables are related, those variables' rates of change are related. So just wanted to restate that. So we'll take a look at example number 1. So notice I have a little cloud around that. If x and y are related to each other, y is equal to 2 times whatever x is, then the rates of change for x and y are also related. And we're considering another parameter, time. So we're taking the derivative with respect to time of both sides. And notice that there is a rate of change on the left and right-hand side of the equation because you have both x and y, and you implicitly differentiate with respect to t. So in this problem, example 1, examining two rates that are related, the variables x and y are differentiable functions of t, time usually, and are related by the equation y is equal to x cubed plus 3. When x is equal to 1, dx dt is equal to 2. Find dy dt when x is equal to 1. So I've already got it set up where I'm taking the derivative with respect to time of the left and the right-hand side of the equation. So on the left-hand side of the equation, we get dy dt is equal to 2x dx dt. So in this problem, we want to find dy dt when x is equal to 1, and we have this dy dt. And we generally say when x is equal to 1, and we could also say when dx dt is equal to 2. So we just say 2 times 1 times 2, and we get dy dt is 4. So our answer, find dy dt when x is equal to 1, dy dt is equal to 4. And we don't have any units on this, so we just leave it go with just the number. Okay, so now let's try one with changing area. So example 2, changing area. A pebble is dropped into a calm pool of water, causing ripples in the form of concentric circles as shown in the photo. The radius r of the outer ripple is increasing at a constant rate of 1 foot per second. You've all done this with water before, right? So let me get an arrow. So it's kind of going out like this, but not only in that direction, it's going out in all directions, right? As that circle gets bigger and bigger and bigger. Okay. And it's a constant rate of 1 foot per second. So the radius r of the outer ripple is increasing at a constant rate of 1 foot per second. So then automatically I'm thinking, well, the radius is increasing. So the rate of change of the radius would be dr dt, the rate of change. Think of it as delta r over delta t, but it's a really small delta r over delta t. And this is going to be 1, and I'm going to put the units over here, foot per second. Okay. When the radius is 4 feet, So now we have R is equal to 4. At what rate is the total area of the disturbed water changing? So now in the end, what we want to know for a question is what is dA dt when R is equal to 4, okay? So we start off with a formula as I have over here. We have area is equal to pi r squared. So what we want to do is take the derivative with respect to time of both sides of this equation. So we have the derivative of area is equal to the derivative of pi r squared. Put some brackets around that. And so the derivative of the area is then just dA dt. And then on the right-hand side, we have the derivative. Remember, pi is just a constant. So then we have 2 pi r dr dt. Remember that we're using chain rule with this because r is some kind of a function of time. So dr dt is the derivative of the inner function f of t. There's an inside function hidden, okay? So now we have that. Now we want to know what is the area, what is the rate the area is changing. And sometimes I do that. I like open up a box and say, this is what I want to find in the end. So it helps me to remember in the end. So when the radius is 4, and we could put the units on. Why don't we put the units on just so we get the units that we know we should get. So it's 4 feet. The radius is 4 feet. And then we have dr dt is just 1 foot per second. So we end up with 2 times 4 is 8 pi feet per second. So we get 8 pi feet squared, per second. So that is our answer for this problem. Just looking at the fact that we want to know how fast is the area changing as the radius is changing at 1 foot per second. You can kind of see if I draw it up here. Let me draw it at a brighter color. If I have a radius coming from the center out when it's the r is equal to, 4. R is equal to 4 feet, okay? So if r is equal to 4 feet, then at that point, the area is changing at 8 pi feet squared per second. So by the second, every second, the area is expanding, but at this time, it's expanding exactly at 8 pi feet per second. Okay, when the radius is 4, not at this time, but when the radius is 4 feet. Okay, so the guidelines for solving a related rate problem are identify all the given quantities and all quantities to be determined. So kind of like I did where I boxed things up right as I was reading the sentences. So we want to make a sketch and label the quantities. In that last problem, the rings or the circles were actually giving me a picture of what I was dealing with. So write an equation that it relates all the variables. In the last problem, it was area is equal to pi r squared. So it was the area of the circles. And the variables whose rates of change. Write an equation that relates all variables whose rates of change are either given or to be determined. Then we want to use chain rule because remember we want to have that doubt or dinner to differentiate both sides of the equation with respect to time. So after completing step 3, substitute in the resulting equation all known values as we did. We substituted in the 1 and the 2 for the variables and their rates of change. Then solve for the required rate of change. Let me just double check to make sure that I did that right. 1 foot per second. And then the radius, I had 4 feet, right? Okay, everything looks good. Okay, so the order of 3 and 4 is important. We don't want to put constants in if they're quantities that are at a certain moment and they're changing. We don't want to put quantities that are changing. So let's look further here. You will often take a statement and convert it to mathematical language. So when we see the velocity of the car traveling for 1 hour is 65 miles per hour. So notice that for instance, like in this one, I'm just assuming that the velocity is positive. It could be negative, but it's not really stating directions. So ds dt, or the change in position over time at that time, is equal to 65 miles per hour, and at t is equal to 1 hour. Then you have the population of bacteria is increasing at a rate of 200 per hour. Now, the rate here is positive. If the word was decreasing instead of increasing, then that would have been a negative rate. So we just say dp, p for population, right? dp dt is equal to 200, and it would be a positive 200. Again, if it was decreasing, if the population of bacteria was decreasing at that rate, then it would be a negative 200. Okay, so let's try a few implicit differentiation with respect to x, y, and t. Okay, so if we do this, we're going to go left to right. ddx of x squared plus ddx of y squared is equal to ddx of r squared. So we get 2x. It is x, so it's just 2x. We're taking the derivative with respect to x. So then we get 2y, and we're taking the derivative with respect to x. So we have a dy dx is equal to 2r, and then we have a dr dx. So when we implicitly differentiate, it's these two quantities that are not x's, so we've got to throw in a dr dx and a dy dx going backwards. Okay, let's take the derivative with respect to y then. Change color here to blue. So if I take the derivative with respect to y, I go left to right, ddy of x squared plus ddy of y squared is equal to ddy of r squared. So I get 2x, and then we have a dx dy, and that's times, and then we have plus 2y, dy dy, which is this one, so we'll leave that out, and then we get 2r, and then we have dr dy. Okay, so using chain rule with that. Notice the chain rule with the middle term 2y was just going to be 1, so I let it go. Okay, then we're taking the derivative with respect to time, so we get 2x. I'm going to skip that middle step there. So I get 2x, then I have dx dt plus 2y dy dt equals, not a plus, 2r dr dt. So again, using the chain rule, and this is because what you're doing when you're taking the derivative with respect to t, and like I said, it's usually time, x is some kind of a function of time, y is some kind of a function of time, and in this case, r is some kind of a function of time. Let's make it h of t. Okay, so you have to think that there's an inside function when you're squaring x, squaring y, and squaring r. You are really looking at something like this, that you have f of t squared plus g of t squared, let me put parentheses there, is equal to h of t squared. And you can see where the functional notation shows you the inside function of each. Okay, so I'm going to pause the video now, and then I'm going to start off with the second video. That gives you a foundation on the topic that we're talking about, which is related rates.